So the last concept for Unit 6 is going to be percent yield. You're going to learn how to calculate this. You're also going to be able to differentiate, not percent yield, but actual yield from theoretical yield. And the most complicated type problem would be this one on the board here, where you're going to calculate your theoretical yield, you're given an actual yield, and you have to calculate your percent yield. Okay, so this is definitions you probably want to write down. So far, we've only been discussing theoretical yield. So these calculations that we do, they are predictions. They are what we expect to happen. All right, they are the maximum amount of product you could actually get. In reality, though, usually you don't end up getting that calculated amount. You get less. All right, and there's a multitude of reasons why that might happen. You might be dealing with compounds that are impure. Based on temperature, some reactions happen faster or slower, so maybe you measure and it's just not done. There's also some reactions are reversible, so it'll go forward to a point, but then it starts going backwards, so you don't actually essentially go to completion. All right, so generally speaking, you're going to end up with quite a bit less than what you actually calculate. And that's where percent yield comes into play. All right, so percent yield tells you the efficiency of your reaction. Okay, so the closer your actual yield is to your theoretical yield, the closer to 100% you're going to have, the more efficient your reaction is. All right, so I definitely recommend writing this down. This is how you calculate your percent yield. You're going to take your actual yield, what you measure and get out of actually running the experiment, divide it by your theoretical yield, what you calculated, and then multiply by 100. All right, so a very simple example of something like this is you calculate that a reaction will create 12 moles of water, but when you run the reaction, only 5 moles are created. What is your percent yield? All right, so I've got you calculate 12 moles. So that's your theoretical yield. And then 5 moles are created. That's your actual yield. All right, so you're going to take 5 moles, divide that by 12 moles, then multiply by 100, and you will get 41.67%. All right, I know that sounds like a really poor percentage, but that's actually pretty normal. There's lots of reasons why you won't complete a reaction to that maximum amount, and especially say if you were doing a lab in your house, your equipment and things like that aren't all that great, so there's going to be lots of reasons why you don't get what you calculate. So another example of how you might be able to use this equation. So a reaction has a percent yield of 60% and produces 500 grams of product. What was the theoretical yield? All right, so this 60%, that's your percent yield. It actually produces 500 grams of product, so you're measuring that. That's your actual yield. All right, and you want to calculate your theoretical yield. So you really just want to plug things in. All right, so you've got 60%, or 60 equals 500 over, I don't know what our theoretical yield is, and that's going to be times 100. All right, so my suggestion to you, because this is going to hopefully this will make this look like something you know how to solve, we're going to move this 100 to the other side. All right, so if I divide both sides by 100, I will get something that looks like this. All right, and I bet you know what to do here. You can cross multiply. So we will have 60x equals 500 times 100. And now I can divide both sides by 60 so that I can solve for x. And that'll be 500 times 100 divided by 60. So our theoretical yield would have been 833.33 grams. All right, if need be, watch this again. You are going to see a question like this on your quiz. And last sort of problem, this one's definitely the longest because you're going to take what we've been talking about, we're going to calculate our theoretical yield, and then we're going to calculate our percent yield. All right, so if you decompose 80 grams of ammonium nitrate and get 13 grams of nitrogen oxide, what is the percent yield? All right, so what we are missing here, what we need to calculate is our theoretical yield. How much nitrous oxide did we expect to get? All right, and we're starting from knowing that we have 80 grams of our ammonium nitrate. All right, so we are starting right here. All right, so we have 80 grams of NH4NO3. I need to get to moles, which means I'm going to divide by the molar mass of NH4NO3. So, remembering on our periodic table, let's see, nitrogen is 14 plus 4 times 1, because there's 4 hydrogens, plus another nitrogen, plus 3 times 16, because that's our oxygen. We are going to have 3 times. Oh, that makes it easy. Our molar mass here is 80, which means we have 1 mole of our NH4, NO3. So now I'm at our molar ratio stage. So we've got 1 mole NH4 NO3. Open up my parentheses. I know I want to put moles of NH4 NO3 on the bottom. And I need to go to moles of N2O. Now looking at my balanced reaction. Another easy one here. Those are both 1s, so that means I'm going to make 1 mole of N2O. And last step, we need to get back to mass because we have to be able to compare it to this 13 grams. So I'm going to take 1 mole of N2O. My molar mass there is going to be 14 plus 14 plus 16. Which is 44, which means I was expecting to get 44 grams. All right, so my theoretical yield was 44 grams. My actual yield was 13. So putting it all together, I'm going to plug in 13 over 44, multiply that by 100. 13 divided by 44. I get 29.55%. All right. So we will practice more of these in live class. All right, but writing examples down, rewatching this, never a bad idea.